Welcome to the introductory video on critical thinking in IT. This session will be on binary numbers. So, what we'll cover is computer data, representing binary integers, converting from binary to decimal, converting from decimal to binary addition, and 2's complement. Computer data is basically any type of information that can be stored in a computer memory and processed. All kinds of information can be stored as long as it can somehow be represented using ones and zeros. Since each of these types of information is stored as bits, how those bits are determined depends on what type of data the computer expects or thinks they are. First thing we look at is representing integers. So an integer is a whole number, not a real number. It can be represented in binary form by writing it in base 2 instead of our common base 10 notation. So in base 10, you would count the digits 0 through to 9, then the powers of 10, like 10, 11, 12, 13, till you got to 19, and you go to 20, 21, 22, and so on. In base 2, you do a similar thing, but you count only digits 0 and 1 because you only have access to the digits 0 and 1 in base 2. Any number can be evaluated using the following formula. The sum from I is equal to 0 to the n d sub I times b to the power of I, where d subscript I is the ith digit, b superscript I is the base or radix raised to the ith power, and the number is the sum of the terms from I equals 0 to I equals n. N is the number of digits in the number minus 1. Binary integers, in terms of their representation, the place of the digit in a binary number gives the power of 2 that the value of the digit represents. The value of a binary number can be read as follows. You will see that the bit position and those represent 2 to the power of something. So the rightmost one is 2 to the power of 0. The second rightmost one is 2 to the power of 1, and so on until you get to the far left one, which is 2 to the power of 7. So the number there is evaluated by looking wherever there's a 1 in the bit value and you count the particular power of 2 at that particular position. So for example, starting from the right hand side, you'll see there's the 1 in bit position 0. That means we have one lot of 2 to the 0. There are no lots of 2 to the 1s because there is a 0 in the 1s column. There are one lot of 2 to the 2 because there's a 1 in the 2 column, and so on. If you were to work those out, you would end up with 128 plus 64 plus 2 plus 1. So plus 4 plus 1, and the answer would be 197, and there's a couple of examples on the bottom there. The first one is 6 zeros and 2 ones would be 2 plus 1, which would equal 3, and so on. Converting from decimal to binary to convert any number n base 10 to binary, we would find the largest power of 2, which is less than or equal to n. Say for example 2 to the x and subtract 2 to the x from n, substitute n minus 2 to the x for n, then repeat step 1 until n minus 2 to the x becomes 0. We then assemble the binary number with 1s in the bit positions corresponding to powers of 2, used in the decomposition of n and zeros elsewhere. As an example, converting 770 to binary, we would find the largest power of 2 that's still less than or equal to 770. So that works out to be 512, because the next one over would be 1024. That would be too big. Since the largest power of 2 that fits into 770 is 512, we subtract 512 from 770, and that gives us 258 left over. Then we find the next largest power of 2, which fits into 258, which happens to be 256. We subtract 256, then we're left with 2. Then the next larger power of 2 that's less than or equal to is 2 to the 1, or 2. We subtract 2, that gives us a 0, and wherever we did the subtraction, we will put a 1 in that particular column, and the binary number that we end up with is 1, 1, and then there are 6 zeros, a 1, and a 0. Terms of addition. How do we add our binary numbers? Well, we add up each binary place and take any carryover into the next column. So here are some single bit additions. 0 plus 0 is 0. 0 plus 1 is 1. 1 plus 0 is 1. 1 plus 1 is 0, carry the 1, and there's a couple of examples of multiple bit addition there down the bottom. 2 plus 4 is 6. 2 is 0, 0, 1, 0. 4 is 0, 1, 0, 0, and 6 will therefore be 0, 1, 1, 0. You're looking at the second one there. 7 plus 12 is 19. You'll see that 7 is 0, 1, 1, 1, and 12 is 1, 1, 0, 0. And there will be a carry in the second column from the left. 2's complement. When representing negative numbers in 2's complement, to represent a negative value x, we take the positive value of x and complement the bits and then add 1. So for example, let's start with a simple one, negative 2. We start with plus 2 and we'll see that that's 6 zeros and a 1 and a 0. We'll complement that, which basically means flip the bits, which means we get 6 ones, a 0 and a 1. And then we add 1, which means we get 7 ones and a 0. We did the same thing with negative 127. We start with 127 and that value is 0 and 7 ones. We complement that thing and we have a 1 and 7 zeros. We add a 1 and we have a 1, 6 zeros and a 1. So that's the long way in terms of doing 2's complement. The simpler way to do 2's complement is to start from the right hand side of the binary number. You find the rightmost one, you keep it, and you flip everything to the left of it. So for example, down the bottom there with the plus 36, you will see that it's 0, 0, 1, 0, 0, 1, 0, 0. You find the rightmost one, we keep it, and everything to the right of it, so we will keep the 1, 0, 0 there. And then everything to the left of it, which was 0, 0, 1, 0, 0, we flipped and we have 1, 1, 0, 1, 1. So in summary, we've considered computer data, representing binary integers, converting from binary to decimal, converting from decimal to binary, binary addition, and 2's complement.